Okay, good morning, good afternoon, everyone. Thanks for being here. So this afternoon's agenda, right, we take maybe 30 minutes to go through all the concepts in gravitation, how they relate to each other. Then we go through the 4-5 questions. I'm not sure whether my time allocation will be accurate. They often prove not to be. I will try. Okay. So let's just go through. I mean, you don't have to copy anything. You can just listen. You want to copy also can. At the end, right, I'll just share whatever I write here in a PDF with you. Okay. So today I will go through, right, a process of creating our own mind map as we go through this revision. Okay. So number one, right, let's start off with the basic of Newton's law of gravitation. So what did this say? Newton's law of gravitation, right, says that the force of attraction, two masses, right, two masses proportional to of their masses inversely proportional to separation. I forgot one word, 2 point masses. Forget the second word, the square of the separation. Okay. Yeah, so keywords to write here, right, is number one, the point mass. Okay. Why point mass is important? Because if they are not point masses, right, there will be dimension. Okay. So where do you take the separation from? So we would like to use point mass in our definition. Okay, to keep it easy. In terms of formula, you have, right, Fg equals to G m1 m2 over r square. I mean, this is really straightforward. Okay, this equation, right, tells us that this is an inverse square law. Okay, you hear this word many times. Inverse square law, right? Anything that has a proportion to 1 over r square. Okay, and so this leads us, right, to the next thing. Suppose, right, we want to talk about the effect of gravity, right, around a mass. We wouldn't always like to talk about just the force, because we want to talk more neutrally. What if, right, we just have one mass, but we want to know the effect of gravity? Then we'll go on, right, and define a second thing, okay, which is the gravitational field strength, right? Gravitational field strength. How is it defined? I would like you to, you see, a lot of people, right, they look at this, listen to gravitational field strength, right? You know what they will write right away? They will say, right, G is equals to Gm over r square. Okay, let me tell you, right, this is incorrect. Okay, because, right, gravitational field strength is not m over r square. Rather, right, it is actually gravitational unit a small is at that point. So what is the formula, so to speak? The formula, right, is actually G is equals to Fg over m. Why so? Because, right, at a certain point in a gravitational field, there could be many methods. Okay, so there could be like 1, 2, 3. Then at this point, right, maybe this guy experience a force generally this way. Okay, force, right, is a combination of the influence of the 3 planets nearby. Okay, and at this point, right, what is the net effect that you experience? You experience this force Fg. Okay, so if you want to talk about the force per unit mass, so it's simply, right, the Fg divided by m. Okay, then, right, the formula that you always memorize and you're very familiar is with, right, is all the due to mass, okay, planet or whatever celestial body, then, right, it will be equals to G. See, so we are still going back to Fg. No space. Let me keep things more to the left. Fg over m due to planet. Okay, so you have a test mass near a planet. So the G, right, it will be equals to Fg divided by m. Yeah. So this is the test mass. Then what's your Fg? Your Fg is Gmm over r square. So you have, right, Gmm over r square. Finally, right, then divide by m. So finally, this gives you Gm over r square. So this formula, right, allows you to use it for the contribution at the point due to this mass. Okay, period. Sometimes, right, you may want to find the contribution due to a few planet, right? So how do you do that? Okay, so let's just use 2 planet will do. Okay, say at this point, so you got to work out, right, the G, right, due to this, let's call this G1, and G due to this, call it G2. How you draw this line to their center? Yeah, then the magnitude of this arrow, use the formula. Then after that, right, do whatever you need to find the resultant. So that is how you use this formula. What about G inside a planet? Okay, G inside a planet, right? Draw this line further down. If you were to see the G inside a planet, normally, right, if we just want to look at the magnitude of the G, or we don't want to care about the direction, right? Later we talk about the direction when we talk about. So outside of the planet, this line will simply be like that. But you got to realize, right, here is a finite slope. So for Earth, right, what's the value of this one? It's just 9.81. Inside of the planet, right, the G is actually a straight line. Okay, how to derive this, right? I think I'll just show you the result. Okay, if you have done the MCQ that I shared with you, right, there'll be some questions that ask you about comparing G of different planet of different density, different radius, that kind, right? So you will come up with G is equals to G pi density R. Okay, essentially, right, G proportional to R inside planet. If planet has a uniform density, then that's like that. But this is not often used, not important at all. Okay, yeah. So how do these two p's, right, relate? These two p's relates, right, via this. Yeah, let me erase that first. Most common application of G, right, of course, right, in this called celestial level. Okay, so we have a non-uniform G. But what if, right, you are really close to Earth, okay, you're really close to Earth, right, then you will have the G, right, which is sorry, you see, I actually never planned how I want to draw, so I will just adapt accordingly. So if you look at the G around a planet, the lines, right, are actually, see, we seldom draw few lines for G. Okay, why? I have no idea, man. But we always draw few lines, right, for electric field. Yeah. So these lines are like that. They're pointing in because gravitation is attractive. But if you actually zoom in, right, to the surface of the planet, let's zoom in a little bit. Okay, so you see this curvature, and where are the lines? The lines, right, are always perpendicular to the surface. So these are the lines, right? If you zoom in some more until, right, you see the Earth level as flat, then these lines, right, become like that. Why not? I mean, as you zoom in, you should see more lines, right? Or you should see less lines. No, it's just represented differently. Okay, so don't mind the number of lines. You see, when you learn in E field, right, you know that the direction of the lines tells you the direction of the G field or E field. Moreover, right, the gap between lines tell you the uniform, the strength of the field. So in this case, these lines are both parallel and evenly spaced. So this means, right, in this region, you have uniform G. Yeah, so you see, these are heights, right, much lesser than radius of Earth. And if you have done the derivation before, okay, maybe in your lecture notes, they will have shown this somewhere in the appendix. Not necessary, okay. Then, right, here the GPE will simply be equals to mgh. Okay, so nothing wrong one. This one, if later we got time, we can derive it. Yeah, but now I'll just keep it as such. Okay, what about the idea of weightlessness, right, pertaining to the oh no, I should talk about it later when we talk about, oh no, we can say that. Weightlessness. Weightlessness, right? The apparent weightlessness is actually an idea, right? That we feel no contact. Apparent weightlessness idea, right? Don't just appear in gravitation. I mean, in fact, right, it's an idea across many topics in mechanics. So it's an idea, right? Saying that how do we feel weight? We feel weight, right? Because we are in contact with our surrounding. I'm sitting on a chair. I feel my weight on my butt. Okay, and I'm standing up for very long in the MRT, for example. I feel the weight, right, on my feet, and I feel uncomfortable, right? Yeah, so we feel weight, right, not because we are not feeling gravitation. We're actually feeling normal contact force. Therefore, right, when we say we feel weightless, okay, we are actually not saying, right, that we are really weightless. We are saying, right, that there is no normal contact force. Therefore, right, all cases whereby normal contact force disappear, then, right, you will have a sensation of apparent weightlessness. Okay, so in summary, right, here, sensation of weight, right, contact force. No normal contact force means, right, apparent weightlessness. Suppose, right, you have a leaf. Okay, we shall just use it leaf, but touch wood. Okay, if the leaf it will snap, then the leaf go into free fall. Us and the leaf both go into free fall. Okay, so we'll feel apparent weightlessness. When you're going in a space shuttle, okay, around Earth, we talk about orbital motion later on. But let's say this space shuttle, right, and the human, you see, Earth, right, gravitation is providing for the, so this is Fg for man, and here, right, is Fg for shuttle. And both of them, right, is equals to the same MAC, yeah. You and the environment, right, both are accelerating at the same acceleration, okay. Therefore, right, both of you by default won't be exerting contact force on each other. And so that's another situation whereby we get weightlessness. Sorry, this is a bit off from the original scheme of talking about the G, but it's just nowhere else to fit it. Okay, let's continue. Let's talk about orbital motion. Okay, and that's perhaps, right, the greatest application, right, of the FTO. We talk about orbital motion. For orbital motion, right, most commonly we have the gravitation, right, provides for centripetal force. Yeah, so let's say, right, you have a planet, okay, and something, right, orbiting around it. Yeah, so from here, right, we can branch out and do two derivation. First derivation, right, if, right, you have the Gmm over, so I backtrack one step. Okay, let's draw in the force. So this is the only force, Fg. You may think, right, why doesn't it fall to the planet? Okay, why can it go in a circle? Why doesn't it fall down? Why doesn't the moon drop to Earth? Yeah, it's because, right, gravitational force that is always, right, directed to the center of Earth. Okay, what is its effect? Its effect, right, is to change the direction of this V. Okay, just nice. Actually, by right, this guy, if there's no gravitational force, there's nothing pulling it in, right? Where should it move? It should actually move, right, tangentially off. Okay, so it's supposed to be, let's zoom in. It is supposed to be perhaps, right, yeah, in a while's time, but it actually never go there. Why then? Because, right, this gravitational force pull it. Okay, so it actually did fall, but it didn't fall, right, in a sense, fall closer to Earth. It simply, right, fall from its original tangential path that is by right supposed to move if there's no force pulling. It falls from that path's next position into the next point in the circular orbit. Okay, you see, where is the fall? The fall, right, is like from, let me erase this arrow again. The fall, right, is from this point, fall into this point. Yeah, so it end up on the orbit again. So you see, from here, it's supposed to go along the tangential direction, but it falls. Okay, it falls from, supposed to go from here, it falls back onto the point on the orbit. Yeah, so that is the role of gravitational force, and that's the role of centripetal force in general. To come back to the definition, right, derivation, Gmm over r square, I use small letter. By the way, capital letter, right, is usually reserved for radius of planet. Okay, small letter is reserved for distance, separation of the radius of the orbit. You see, because our FC, right, got two forms of mr omega square or mv square upon r. So we will do one form first. So let's do mr omega square. And omega square, right, we can rewrite it as mv square upon r. Is it mv square over r? m2 pi upon t whole thing square. Okay, so rearranging the term, mainly, right, cancel away the m, then, right, you'll see, sorry, I am missing one r. So the r bring over, the t square from the bottom bring over as well. So you'll see, right, that square is actually equals to, let me make sure I got all terms right, 4 pi square. Did I get it right? No, sorry, 4 pi square gm times, so from here, right, you can see that t square is proportional to, this tells you, right, things that are going in orbit. Okay, larger the orbit, the longer the period. Okay, is it always? Yes. Okay, when can you use this? Only for orbital motion, nothing else. Then the other form, Gmm over r square equals to mv square upon r. Some of you may feel that all these things still look alien to you, because you really haven't done this enough times. So you need to get a pen and paper, right, go and derive it, or you need to practice. Then you gain confidence. Okay, so with this, right, you can have v square is equals to gm upon r. Okay, v, right, is proportional to 1 over square root r. So the smaller the radius, the faster the thing moves. Okay, so these are the main two relationships that you need to know. What else here? Okay, from here, right, we can go on and talk about the energy of orbits. Okay, energy, right, you have, of course, right, and you have PE. And what PE? GPE. Together, right? Total energy. Let's look at the KE first. KE, right? From this equation, okay, you can rewrite it a little bit. So let's times a half times a R to both sides. So you have, right, half mv square, yeah, mv square times half times R. Right hand side times half times R as well. So GMM over R. Okay, here you can see, right, that the left hand side is a KE. Right hand side, right, looks very similar to GPE. Yeah, it's actually, right, minus, as GPE is minus GMM over R. So this one is actually minus. So if you want to find the total energy, right, is equals to KE plus GPE. Left hand side you will have GMM over, the first term you have GMM over 2R plus minus GMM over R. Okay, together, right, they give you minus GMM upon, okay, so this is, right, equals to minus of KE equals to half of GPE. So you need to know, right, these three are always related as such. Drawing the graph, this graph, right, y-axis is energy, x-axis is R. This is the radius of the planet. For obvious reasons, right, the satellite cannot orbit like into the planet, right? The smallest radius it can have is just above the planet surface. So how do you draw the three graphs? Let's draw the GPE first. GPE will be this one. Okay, take note here, right, it's not an asymptote, or it's a finite value. Okay, and this is a 1 over R shape kind of graph. So this is GPE. Total energy, half of this. So this is total energy. KE, mirror image of total energy. So observation from this graph. This graph is can give us a lot of insights. Whenever, right, satellite, right, loses due to friction, for example. Why due to friction? Rub against what? Yeah, some of the satellites, right, are in orbits, right, not too far, not far enough. Okay, so there's still a little bit of atmosphere there. So that's one way. So when, let's say, right, satellite loses energy due to friction, right, so what energy it lose? Okay, it's actually, right, total energy will decrease. Yeah. So you look at the total energy, right? If the satellite was originally at this value, decrease means what? It moved down the slope. So it will get to a value, right, that is further down the slope. And what will it mean? You mean that you go from a certain initial radius, as you go in a circle, right, or circular motion, its radius, right, will decay. Yeah, radius will decay. Means, right, radius drop. And what happened as the radius drop? So you see, you plot out the corresponding point, right, for KE. So you mean, right, that the KE, right, actually increase, whereas the GPE decrease. So what's the consequence of a satellite, right, losing energy due to friction? Well, it actually gets faster, strange enough, right? And that's definitely opposite to our intuition, because normal things, right, when they work against friction, they get slower. But this satellite actually get faster. How do we explain this? It's because, right, you see, this guy got faster, you see. Suppose, right, you walk on the street, okay, you drop $50, okay, you didn't know that you dropped $50, but someone behind you told you, hey, you dropped $50. Then you go put your hand into the right pocket and touch money, right? Hey, my right pocket, right, end up $50 more. Yet, right, that person tell me I dropped $50. Then you go into your left pocket, then you realize, my left pocket, right, suddenly missing $100. So it is actually, right, GPE loses 2 parts of energy, and at the same time, KE gains 1 part. So the net change, right, is you lose 1 part. So for every 1 part of energy that you lose, that is actually 2 parts of that's actually made up of 2 parts of GPE loss and 1 part of KE gain. So this is the interesting thing for the energy of satellite. So whenever we come across such question, right, so this is something that you need to be aware of. How will the motion look like? It will look a slow, steady spiral. Okay, it's definitely not an aggressive spiral. It will be a slow, steady one. Usually, satellites all lose energy, and they need to correct for this loss of energy, but it will be a slow process, not something that happens, right, very fast. Let's talk about types of satellite. Okay, hey, let me take a break, okay, because I put something on the stove to cook. I need to turn off the fire. 10 seconds, I'll come back. The thing I cooked, 炒大料, salvage later. Okay, so we're talking about the types of satellite. Okay, first one, right, most important is always, right, the geostationary. Okay, so geostationary, right, some students don't get it. It is appearing, right, to be always, right, above a certain point on Earth. Okay, so let's say, right, this is the axis of rotation of Earth. So Earth, right, rotates which way? You got to realize, right, we see sunrise from the east. Okay, so Earth is actually rotating west to east. Yeah, so if there is a distance object, right, the east side will be the turns and see the distant object first. That's what is meant by sunrise. So this rotation, right, is this way. And I meant the North Pole as there lah. So Earth's rotation is this way, and this omega, right, is or rather, let me just put period. Period is 24-hour, right? How does something appear geostationary? Number one, right, this satellite must be orbiting, right, in the same direction as Earth. As Earth turn this way, satellite also turn this way, so that the satellite, right, always above the person observing it, right, in the sky. Okay, if the satellite turn the other way, then the satellite will disappear from your sight. So first condition, right, is rotate direction. Next, right, you got to realize, because Earth rotates about the axis, right, that almost runs through the pole. The equatorial plane, right, is the plane that rotates the most. Okay, and if you want to park a geostationary satellite, right, and you want it to be observed by a person on Earth, right, this satellite must share the same plane of rotation as the equatorial plane. Lies on, okay. Number three, right, of course, has period 24-hour. So three conditions, right, all must have. Then can be geostationary. Sometimes, right, you look at the sky, right, don't think that's geostationary, but yeah, there's always geostationary satellite in the sky, but geostationary is always very far, so we are not likely to see it. Yeah, it's always in the sky one. At night, right, if you happen to have a very dark day, maybe you can see it. Okay, there's always some geostationary satellite in the sky. Daytime you cannot see, it's still there. Always above. Interesting thing to note, not just interesting, right? I think it's important to know, right, that the radius, right, if you have done your calculation, okay, so if you have solved for GMM over R square equals to MR 2 pi over T, okay, whole thing square, and you sub in 24-hour here, right, the radius of this satellite, right, will turn out to be around 42,200 kilometer. Okay, so this is roughly, right, 7 times radius of Earth. 7 times radius of Earth. Radius of Earth is 6.4, 6 point something times lah. Yeah, around there. So whenever you do this calculation, know this so that you know, right, whether your calculation can make mistake or not. It's around 7 times. Wouldn't be off one. There's only one geostationary satellite orbit, no second one. Okay, then the other less important one, right, for example, is the low Earth orbit. This one is called LEO. Low Earth, right, means what? Okay, the Earth orbit, and geostationary is the high altitude already. This is really far. Let's compare, right, their characteristics. So when you have low altitude, right, the main thing, right, is that it's near to Earth. Yeah, so the transmission, right, that you see when you have a satellite there, you want to transmit information from Earth to the satellite back to Earth. Okay, you know, right, from wave topic, right, the intensity of wave is equals to power over 4 pi R square. Yeah, but satellite usually don't transmit in a omnidirectional way lah. But still, right, we can say that this is a power proportional to power over R square. Still must be some R square relationship. Okay, if you want to receive the signal at the same intensity, it's either, right, you have a greater power compensating for a larger radius, or if the satellite cannot generate enough power, right, this will be a very light duty one, not a heavy duty one, then, right, and it can't project very powerful signal, then it should be nearer. Okay, otherwise, right, you can't receive the information. So the signal, right, will be low altitude. Signal generally, right, stronger. And if you are taking photo of Earth, right, you can take better resolution photos of Earth lah. If you are taking photo of the universe, right, doesn't matter. All about the same. Yeah. Lastly, right, lower cost, yeah, obvious, right, because don't have to launch too high. High altitude, okay, what advantages? Usually, right, it means that you can have greater coverage, and also, right, another advantage probably is because it's higher, so the air is really thin, almost no air already. Okay, so no atmosphere. So you don't need to worry about atmospheric drag. Atmosphere. Okay, so these are the things to know about. Let me see whether I miss out anything or not. Never mind. Okay, we just go on first. If I miss out, can come back to it later. Okay, just now I already casually mentioned the formula GMM over R. U equals GMM over R. So let's launch more deeply into the idea of GPE. GPE first up is definitely the definition. And before I do definition, I need to teach you or help you revise conservation of energy concept. Okay, so you see, I believe some of you you have been through my lesson on the ways to express a COE statement, especially how you relate work done, okay, the external work done, and the total energy. So one of the statement that we can write is net work or work done by external force is equals to the change in total energy. And change in total energy is what? Is equals to change in KE plus change in PE. For this case, we will just have GPE. Suppose, you have a situation whereby, as a result of doing this work, this object, actually never get faster, never get slower. We didn't change its KE. We kept this KE the same. So change in K is 0. So this net work done, will be equals to what? This will be equals to GPE final minus GPE initial. So let's keep this as such. We'll come back to this in a while. So let's go through the definition of GPE. Then we will understand why the definition is shaped in that way. So the GPE is the work done, external force, bringing a test, okay, from where? Infinity to that point in, okay. So this is the definition. Why is it like that? Okay. What is the GPE that we want? The GPE that we want, the GPE at a certain point is actually this term here. So if we make this GPE GPE at that point, then this process involve what? Involve us bringing something from infinity to that point. So here we will have if you rearrange the B work done by external force plus the GPE at infinity which is the initial, which is the infinity, correct or not? Okay. We want to say that the GPE is the work done by this external force, bring the test mass from infinity to that point, without changing KE. So this will mean that the work done, we need to study what is the nature of this work done. So let's draw in the Earth. Okay. This infinity, this is where we start from. The mass starts from here. It goes in. Gravitation is attractive, but at infinity don't have yet. But once it's not at infinity, then you'll be pointing in and larger. Work done by external force, why do you need a work done? Because you don't want it to change KE. So what you are trying to do, is actually to try to prevent it from speeding up. So your external force, will just be large enough, to be equals to the gravitational force, so it doesn't speed up. Yeah, and turns out that you're actually serving this external force is serving like a braking force. Okay, prevent something from speeding up. Yeah. Therefore, what's the work done? The external force point outwards, but the displacement is inwards. So this work done is always negative. Plus, we also want to take the infinity GPE. Therefore, GPE. I shouldn't say therefore because here we have let me write GPE always negative. The 3 points to support. Number 1 point is gravitational force attractive in nature. This is to mean therefore our external force is pointing outwards. And number 2 point is work done by external force direction F external and the displacement. Okay. Finally it is because our infinity taken. So these 3 points together plus our statement on the left, or how does it match? This point illustrate this. Okay, this one is negative. And why is this point negative? Because gravitation is attractive. Therefore, the F external is opposite to gravity. Actually, the first point also helps to elaborate this. Then finally, GP at infinity is taken to be 0. So this point, right, supports this one. So we're saying, right, this is 0. Then work done by external force is negative. So what's your GP at that point? Negative. This one will be heavy, right, on people who learn it for the first time. But just have to go through this set of a few times, and then you'll be okay. So what will be the corresponding twin, right? Not say twin, the cousin, okay, of the GPE, of just like what gravitational field strength is to the force, is therefore, right, the idea of potential. Okay, just like, right, at a certain point in the field, you may have, right, field strength, which is the gravitational force per unit charge, per unit mass. Similarly, right, due to many masses, right, of this object that is in a gravitational field also have a gravitational potential energy. So more generally, right, gravitational potential's definition, right, per unit mass. Okay, yeah. So phi, right, is equals to U divided by G. Okay, U divided by G. U divided by M. Sorry, I made a long mistake. What about the G, right? What about the U to two masses? Okay, how do we have that formula? If you have understood this definition, right, then the U for this process, right, is simply equals to minus GMM over R. The exact reason why this is so, right, you need to do an integration, because you need to find the work done by this external force. We don't need to know how to do that. We just need to know the result. Therefore, right, due to a certain mass, okay, contribution due to a certain mass, right, of a certain, then you will have the phi, right, as equals to the U divided by the G minus GMM upon R upon M, so minus GM upon R. Finally, right, we come to linking of force and potential. Okay, this part, right, is actually very, very important, and often, right, students fumble here. So you see, what is the relationship between force and potential energy? It is actually, right, given by gravitational force equals to minus du over why so? Because, right, U is actually equals to the, you see, this is the work done, gravitational potential, right? Potential energy is work done by the external force, right? So I still have to show it again. From infinity to that point. Fe is equals to what? Fe is E external, right, is equals to minus Fg, because it's simply opposite to Fg. So you end up, right, with this thing to integrate. So you are actually integrating, right, from infinity to R, GMM over R square. Okay, so when you integrate the R square, so this gives you this equation. Back to here, right, that's why, right, Fg is equals to minus du dr. So we are just looking at the differentiation form of that relationship. Is it U equals to the integration of Fg dr. So Fg equals to minus du dr. With this, right, it's telling us, right, whenever we see a U against R graph, take the gradient, okay, and take the minus negative of the gradient, that gives us a G. And that will also give us information about the direction of, we'll talk about it, right, in the context of some example. Correspondingly, right, you divide by mass on both sides, you get G equals to minus the phi over R. Okay, so these two equations, right, links up the energy side of things and the force side of things. Left hand side, right, you see, this is a force. This is a force per unit mass. This is a energy, or this is a energy per unit mass. So whenever you want to articulate, right, like what is potential or what is field strength, you don't come up with a new thing, okay, to say it, because, right, it's actually the relative of something that you are very familiar with. Strength is just force per unit mass. Potential is energy per unit mass. Okay, with this, right, let's look at some common example. Okay, some common application. Number one, right, is escape velocity. Escape velocity, right, is the situation whereby you launch an object, right, with a certain speed. Okay, it could be from Earth, but it doesn't have to be from the surface. It could be launched from somewhere in mid-air or away. But typically, we launch it from Earth's surface and want to launch it to infinity. Okay, so for such a problem, right, and for many situations in gravitation, it's always looking at conservation of energy. So you want to get this guy there. Assume, right, during the process, there's no resistive force. Okay, no resistive force means what? Means, right, total energy remains constant. Then right, you can apply by COE. KE initial equals to KE initial, GPE initial equals to KE final, GPE final. Suppose right, you just want to launch this guy with enough speed such that it escape to infinity. In this kind of diagram, right, it's not correct to label a point as infinity, because infinity simply cannot be labeled out, or it's just very far. But we'll just deal with this inadequacy. Okay, cope with this, just accept it. Okay, represent it with this defect. This guy goes there. You want it to just nice go there. You don't want to waste energy, right, so to speak. You don't want to launch it with too much KE such that you go there, it still has some KE left. Just like, right, let's say you want to throw a ball over a wall. Okay, you want to just nice throw this ball over this wall. You don't want to throw this ball with too much KE at the beginning such that it fly high over the wall. You just nice reach the top of the wall only. So that's the same idea. When you launch it such amount of energy, it just nice reach. Therefore, right, when you reach infinity, this one, right, will become 0. Okay. GP at infinity is also 0. Right hand side all 0. Left hand side is what? Half mv square plus minus gmm over r square. Over r, sorry. So you solve for the v. So the v, right, will become what? M and m cancel out. 2 times over. So you have 2gm over r, putting square root. Okay. This form, right, can be further simplified or re-represented, okay, by something like this. You notice here has a 2gm over r. So suppose, right, I want to make the small g appear, which is the field strength on Earth's surface. So I can have, right, 2gm over r square by times r. So this will make it, right, what? This will make it 2gr. And take note, if we are starting from Earth's radius, then this will be RE. This will be RE. So this is another formula, okay, that we write it as. It's telling us, right, the stronger the G, the harder, the higher the escape speed needed. The stronger the G, the larger the escape speed. Another application, not say application, another situation, right, that we study and appears very often is Earth Moon. So let's draw out an axis, right? Earth is here, Moon is here, and as always, right, we draw things only from surface of the planets, because we can't really go inside. So first up, right, let's draw out the potential, okay, potential due to these two planets, okay. So potential due to Earth, right, will look like this. Why much bigger mass? Whereas that's due to Moon, right, will look like this. Okay, so if you draw the net potential, right, it will look like this. At this point, right, it will be double the negative value, and then, right, close to each planet, you will adopt the value that is bigger, or close to that value more. So this is the net. Okay, so y-axis is potential, x-axis is r. So let's apply, right, the idea of let's understand this slope first. What is this telling us? This is telling us, right, that actually know the value. I think, right, this is minus 62. The power, I forgot how much. I think, right, this is around minus 4. I forgot the power. Is it 10 to the power of 9 or something? Okay, so simply, right, it is telling us it is easy for a object, right, to go from easy to go Moon to Earth, go from why? Because, right, to go from Moon to Earth, you only need to get from this point here, this entire potential graph, right, think of it as a hill, okay? So if you want to roll to the other side of the hill, right, starting from the side of Moon, all you need to give it, right, is a small little nudge and a kick, okay, such that this guy, right, can reach the top. Just once you reach the top of this slope, right, this hill, you can roll down the other side, spontaneously. So the part that's difficult is only the first part. Therefore, right, you see, going from the bottom to the top is easy from the Moon side. Going from the bottom to the top, right, is difficult from the Earth side. And, right, what is the energy needed? It will be the potential, whatever this value is. This side is this difficulty. So you need to have m times this delta phi of energy. Whereas, right, on the other side, m times the other delta phi, which is different. How do you relate, right, this graph to force? Okay, to force. One way, right, is of course to just analyze the forces acting on these two, which we'll do first. At various points, right, you see, let's say at here, let me put in the neutral point as well. So near Earth, right, Earth obviously have an upper hand. As you go further, is going to be shorter. Near moon obviously have an upper hand. Some point here equal, and after that becomes shorter already. So you can expect, right, the net at this point will be this way. The net at this point will be this way. The net at this point will be 0. The net at this point will be this way. So let's say, right, if the right hand side is positive, then right, this G will be negative G, okay, all the way until here. Because right, all this G is going to the rest, right, here is all. So this is one way of seeing it. You reconcile it, right, with the equation G is equals to minus d phi. You get the same thing. Okay, we look at this gradient here, right? You see the green color line. On the left hand side, right, the gradient is the steepest, and it's a positive gradient. Means what? Phi the G will be negative. Positive gradient with the negative sign here will have a negative G. And as you go up the slope, the gradient decreases. This turning point here. So this gradient, right, at first is the largest value, smaller until this point. Then after that, bigger, then become rolled up green line on the other side, negative gradient and getting larger to the right. Okay, convert into the G times a minus sign, right? G become positive. So it's simply a graph that is like that. Yet one more way of looking at it is that along this line, we have two G competing with each other. G due to Earth is like this, 1 over R square graph. So this G due to Earth. G due to Moon is like this. Okay, the graph is much lower because Moon's mass is lesser. So you combine together at the neutral point, right? These two G are equal and opposite. Yeah, so they cancel out. Yeah, so this is all that I would like to cover for the basic. Okay, and I just realized, right, I've overshot my time. Not to worry, we play by ear. So let me go to the question solving. But at this point, right, let me just check any question from any one of you. Okay, let's look at the questions. If you have done right, then you realize it's not difficult. Okay, I'm not going to go through every part in detail. A lot of it is calculation. So calculation, right, I leave you to work it out. If you made a mistake, figure out your mistake. Okay, so I'll go through more like from a examiner perspective. If questions, right, came out in exams, what did the markers say about all this? Okay, so these are like from the past year exam paper, so we know the markers say. Okay, so first part, right, let me toggle to the right question. The definition of Newton's law of gravitation, this one I think can skip, mentioned it already. Show that the period is proportional to R to the power of 1.5. The only thing that I would like to say, right, teachers have said thousands of times, it's always right. Gravitational force provides for centripetal force. This definition, if you don't know, right, please go and work it out until you are very familiar. Okay. I'm surprised, right? Some students until JC2, until A level, still cannot do this. And guess what? If these 3 marks appear in exam, right, it is meant to be a you should put inside your pocket. I'm very happy that this come out. Next up, when we were given information about the Iridium satellite and the geostationary one. Okay, we know geostationary is 24 hours. Is it stated in the question? Not stated, but we must know. Hence, right, once you have the relationship, proportional relationship, right, which is like this, you can always do the next step already. So we see if it's proportional, T1 to T2 will be equals to R1 to R2 whole thing. 1.5 times 1 to the power of 1.5. Use this proportional relationship, work out the ratio. You get Iridium's radius as 1.69. Okay, no need to convert to second because look at the unit here. They're asking it for hours. Here I think most questions are okay. Most students did okay for these few parts. Next up, right, calculate the speed of the satellite in kilometer per hour. Actually, right, if there are students who didn't do okay, out of the carelessness, right? They saw the snake, right, but add the legs. Okay, yeah. So this part you also don't need to go and do any conversion because, right, already in kilometer, and your period is already in hour. So this already give you kilometer per hour. Don't go and expand it out and later on convert it back. That's really dumb. There are students who actually do these things. Okay, some students did all the unnecessary computation and convert back again. One modification to the orbit, right, in order to increase the duration for the time window. This idea of, right, the satellite must be line of sight to the Earth, right, is always, right, tested in this kind of explanation or suggestion kind of question. You see, the satellite is useless if, right, you cannot talk to it. And how do you talk to it? You must have a direct line of sight. So you want the satellite to be somewhere in the sky or above your sky, or not the other part of the Earth. Yeah, or the sky in the other part of Earth. You want it to be above you. How do you want to increase the time radius and the time window? One way, right, is to change to a elliptical orbit. This one you may not be very familiar at first, but once you've done a few times, you'll be fine with it. Elliptical, right, means like this. I will explain why this is leads to a more time in the next question. Okay, if you are here, right, you see, most of the time this satellite is most of the path of. But how do you know that this is confirmed true? I mean, in terms of why must a bigger sector correspond to a longer duration? Talk about it in the next question. Okay, so now let's take a look at the next one. First part. At this part, we will skip, okay, because we have done it in details just now. So let's skip all the way until here. Part 3. The Yamao is certain mass, certain orbit, right? So on. So when it is near its end of life, we want to shift it to a higher orbit. How do we find the energy needed, right, to make this transfer? This is actually very straightforward because earlier part we already calculated the total energy of orbit. Take note at this point, right, this formula, right, the total energy equals to minus GMM over 2R, and KE equals to GMM over R. Sometimes, right, students frivolously use this formula in other situations. They may be required to find KE of some sort, okay, maybe escape velocity or whatever, right, other scenario whereby you need to have KE. And students, right, clumsily just use this. You see, what is context for this? This context, right, is for in orbit. You cannot use for things which are not in orbit. For example, you want to launch something, right, to escape. That is not in orbit, that's stationary on Earth. Yeah, so you cannot use this kind of formula. Okay, so you must get things in context. Back to here, right? Since you already found the total energy, this formula, original Yamao satellite, right? That original orbit have a total energy associated with it. You want to shift it higher? Yeah, can. Or you have another total energy associated with it. And you remember the graph, right? It's like this one. The total energy graph is, so if this is your original, let's call it initial, this is your final, and you want to move it to this final, right, okay, which is further, it means, right, total energy will increase. That's why we need to have energy provided to it. And since this total energy increase, right, so we can simply, right, put delta ET. This will be a positive number already, because you will not be afraid, right? This number will be negative because it's increased. You have GMM over 2R, right, minus GMM over 2R, for R initial, and minus the minus GMM over 2R for R final minus R initial. But because you have a negative sign for this formula, so you can flip the R initial and R final. So we take out all the common term here, leaving only the 1 over R inside the bracket. This should be always done. So do not, right, pre-compute. So take out all common terms. In fact, right, I will also like you to do another thing, okay, for such computation, right, a way to make you have a higher success rate. Even, right, for the denominator, right, I may want to pick out this 10 to the power 7. I will want, if I were to key in calculator, what will I key in? I'll key in 1 over 4.22 minus 1 over 4.25, okay, yeah. So this is my calculator. Then, right, this first step. Then, right, you will have, right, second step, right, then times the 6.67 times 5.97 times 1870. Okay, this is my second step. Then finally, right, my third step will be times 10 to the power of minus 11 plus 24 minus 7. So this is what I really want to do. I don't want to pre-compute term by term, okay? You do that, right, you often will make mistake on. And I believe a lot of students, right, they have low success rate in some of these topics that involve this kind of heavy constants, right? It's because they cannot even press calculator properly or make mistake. These are tricks, not fundamental, but make a difference to your score. Next, here comes, right, the reason why elliptical orbit, right, spend more time in one half. Okay, so question asks, right, as a satellite with ammonia orbit move from P to Q, its speed slows down. Or why is this so? So you see, going from P to Q, right, the obvious difference is the cross radius. Yeah, because you can't really say that it's a radius because it's non-uniform, right? But you can still say that R, okay? So this distance, right, decrease as you go there. Sorry, increase as you go there. Therefore, right, GP increase. And since, right, you never go and disturb this satellite, you're just letting it move by itself, right? Total energy remains constant. And that must mean, right, KE must have decreased. Therefore, it slows down. Some students, right, didn't mention total energy remain constant, okay? Some students don't know how to start, yeah, but it's actually not very difficult. You see, this whole question keep on talking about energy of satellite. By now, right, you should have known it must be related to that. So you must have guessed, right, look at the P and Q, compare GPE, then what can you say about the KE? Since, right, on this side of the, let's say Russia is here, more sensitive, as it goes from here in the far, big far loop, right, or the far part of the loop, or it's always above Russia, okay? And what happened is KE is actually smaller and smaller. So speed, right, or velocity is actually smaller. The loop, this part of the loop is bigger. So you have a smaller speed, more distance to cover. Therefore, you spend even more time as a fraction of your whole period, yeah, above the Russia. Therefore, right, this thing is good. I mean, Russia launched, right, to serve who? To serve Russia, what? Or do charity, launch it so that it can be always above Africa or what? In the serve itself. So you want the satellite to be above the northern hemisphere for more duration, more percentage of the time. Okay, next question. We have this question, right, on the potential against R graph. Okay, this is a common type of question. And you see here you have two stars. Okay, and therefore, right, you see the curve, right, is as such. You could notice, right, somewhere here there's a neutral point. And once again, it is easier for the object, right, to go from one side to the neutral point than the other side to the neutral point. Yeah, so easy to go from star B to A, difficult to go from star A. Okay, so let's see, right, what the question asks. Question asks, right, determine the magnitude of F, right, determine the magnitude F acting on the rock when it is at S equals to 0.1 times 10 to the power of 12. Some people, right, they do this question, I don't know how, but they somehow GM over R square. Okay, how? There's now no information for you to do so. Okay, I guess, right, their thinking was, right, they will take this value. Okay, they will take this value. What does it happen to be? Somewhere around maybe 0.12. Some students, right, they will, and the Y value is like -9. So they will take -9 equals to GM minus GM over 0.12, because with the power of 10. Okay, to go and calculate M, because they think that this is the contribution due to one planet or to the star A. If you do this method, right, confirm wrong one, even if you can get an answer which is pretty close. Because, right, number one, this question not set to test this method. So this method is not in the mark scheme. You'll get it wrong. Number two, right, this formula is not applicable already the moment you have two masses, because at every point there's a contribution due to both masses, not just due to one. So you should not do that. Yeah. Instead, right, once you see a graph and you see a phi against R graph, definitely, right, is to use the G equals to minus d phi over dr relationship. So you draw the line, find a gradient at the at this point. Yeah. Then you go on and times the mass, because F equals to M times G. Then what about the direction? You see, this gradient is positive. Yeah, means, right, G equals to minus of the gradient equals to negative, point towards A. So that is what the angle, the negative sign here means. And positive, right, for all such question is following. So this is the convention for positive. So the axis, right, tell you which direction is positive already. So we have negative means what? Opposite to where the axis point, which is to the left. This part we explained it before already just now. You can just pay attention to later. Take a look at this answer, right? See how we phrase it all out in a exam context. It's 3 marks, but it's very hard to phrase. Okay, this one feels like more than 3 marks. We want to determine the minimum speed, right, that the rock reaches the surface of B. Okay, reaches the surface of B. We launch the rock, right, from surface of A. Okay, look at the diagram again. Launch it from the surface of A. want to reach B. So what is the KE required? Going by our logic, right, the KE required for this rock to reach B is simply, right, the KE required for this guy to reach the top of the slope. Once he can reach the top of the slope, he can roll down B already. So what we will do here is to find the difference. Here you see this is minus 4.4, minus 4.4. Then here initial one is how much? Around minus 8.8 or minus 9. Up to you how you read off lah. So the difference, right, is how much? Times 10 to the power of 8. The loss in KE equals to the gain in GPE. You want to find the speed, right? Gain in GPE equals to mass times this is equals to what? Mass times, because it's a gain ma. So mass times delta phi. The delta phi will be the 4.4. Did I make a mistake here? The 10 referring to. Let me just check my own working. 1 minute. Oh, no. Sorry. I read wrongly from the graph, right? I think it's hidden by my gradient. The graph, right, extends until somewhere here. So it's like 10. So 10 to the 4.4, right? This is how much? More like 5.6. So that's where the 10 and the 4.4 comes about. Yeah. So this is the 5.6. Okay. Calculate out. Don't make any mistake. 3.3 times 10 to the power of 4 meter per second. Finally, right? How would the graph of KE against X looks like? Yeah. So it will simply, right, be a curve. Okay. So you see, as you roll up the slope, you will lose KE. Then on the other side, you'll gain KE. And in the end, right, you must have gained more KE than you lost, because the other side of the slope, right, is very deep. So you have rolled down a great deal. Therefore, your KE will have shot up on the other side. And the minimum value, right, you should just keep it as minimum. Okay. Because, right, let me actually say this. The rock has a speed that's larger value than calculated. That means, right, it can more than reach opposite side or more than reach the top of the slope. Therefore, at the top of the slope, you'll have a KE minimum. So that is how this one looks like. Final question. One more question, right, on those kind of two planet system. Why? Because this is really common and a lot of concepts can be covered, right, in such a question. Explain what is meant by the neutral point. Well, it is the point where the gravitational field strength, you see, we want to express the across, right, to the examiner, right, we understood this. So G due to Earth, G due to Moon. Yeah, basically these two are equal at the neutral point. G field due to Earth equal in magnitude, opposite in direction to that due to Moon. Yeah. So next part, we are supposed to determine, right, potential at the neutral point. How do we know? Question tell us, right, the 1000 kg spacecraft needs this amount in order to reach the neutral point from Earth. What I didn't draw is like this. Earth, right, is minus 62.3. Neutral point, right, is okay. So this is question mark. But we know, right, that the delta phi times the m is 6.1 times 10 to the power of 10. This equation, right, is reenacting this graph in terms of the calculation. So 6.1 times 10 to the power of 10 equals mass times the delta phi. Thereby, I could find what is the potential at the neutral point. One thing, right, you could do to check your answer, make sure that your answer makes sense, is, right, compare this neutral point potential with that at Moon. Okay, that at Moon, right, is equals to what? Equals to minus 3.9 times 10 to the power of 6. Clearly, right, that at neutral point must be higher than, because otherwise the neutral point has to be higher. So this value here, right, have to be higher than both potential. So you can check using against the value for Moon. Because it's confirmed higher than Earth, but it must also be higher than Moon. So if you made a mistake, right, in the calculation, you could check and realize it. Find the minimum KE to launch something from Moon to Earth. Okay, so it's just a reverse of Earth to Moon kind of process, right? So you'll use the Moon's value, the neutral point's value, times the 1.4. Okay, that will give you the minimum KE necessary. Finally, right, come to a binary star problem. In a binary star, right, this part is always, right, not easy for students. Number one thing, right, is they attract each other with an equal force of 1 on 2, 2 on 1. These two forces are equal. Sometimes students, right, they got confused. These are action-reaction pair. Where is their center of mass? Suppose, right, you have let's just use a general example and learn how to figure out. You see, let's say this is 3m. I always, right, think about the center of mass, right, as the point on a satay stick, okay, that goes through these two fishball, okay. this statistic put through these two fishball. The point here, right, whereby if you try to balance it, it can balance. You got two fishball, one big, one small. So this point is your center of mass. And how do you determine that? So it is, let's say you call this R1, this R2. So 3m times R1 must be equals to m times R2. So you can hence tell, right, that the R1 is to R2 is 1:3. So it's the inverse proportion to their masses. And you can verify, right, for this question, it's indeed true because 2m and m, so the neutral point, the center of mass, 1/3 way from 2m, 2/3 way from m. So it's r and 2r. Total distance between them is how far? Between them, right, is, so for each of them, right, the centripetal force is providing for the gravitational force is providing for the centripetal force. First part, you already found out an expression for the gravitational force. You put it into the equation here, okay, equals to mr omega square. You already know the omega, because you know the period, and we solve for the r. By the way, right, I want to explain why they will have the same omega, because it's taken to be as such. Let's say we look at say for mass 1, yeah. So you have, right, 2mm, the r is 3r, okay, 3r square equals to, since we're talking about m, right, on the right hand side, the m is simply the m, not the 2m. And then the r is what? The r is 2r, because, right, this guy is 2r from the center of mass, about which they spin. Assume, right, they have a different period, okay, and different omega. So they just label this as omega 1. For 2m, right, you have gm times 2m over 3r squared. So you notice, right, right hand side, sorry, left hand side, these two are same. Right hand side, you will have, right, times r. We are talking about 2m here. How far is it from center? R. And let's assume it has a different omega from the m, or call it omega 2. Turns out, right, here you have a 2mr. Here you also have 2mr. So you see, this is same. Therefore, these two also same. So they must have the same angular. So this part just doing the calculation. Now this is a 20 mark gravitation question. So you see, there's a lot of different kind of question tested, different kind of concept tested. At first is the gravitational potential, two mass problem. Then after that become a binary star problem. Finally, right, satellite problem. Qualitative one. Validity of the statements. First one, student A claims astronaut floats. That's why 0 weight. Wrong. If she floats, right, but that doesn't mean 0 weight, because there's always gravitational force which provides for centripetal force. And gravitational force is what? It's the weight. So float doesn't mean 0 weight. Second one, astronaut floats because both astronaut and capsule have same centripetal force. No, it's both are in the same orbit. They have the same centripetal acceleration. But since, right, mass are different, so centripetal force, which is equals to MAC, also different. That's it for today. Any question? Do I still have any audience left? Or all left already? Wow, still got 6 participants. Not bad. These questions, right, are not the difficult ones, and I don't believe, right, it will be helpful for you. Because I already said it's pitch at the average student, right? I don't think it's helpful for you to do difficult ones. You do all these 4 problems, right? If you caught it, okay, understood from your mistakes, understood the concepts better, right? Good for you already. This is the on average, right, how gravitational questions will be. Hopefully, right, after this experience, you no longer feel that gravitation is fearful. It is understandable or comprehensible, and you can master it on. So if you have no question, right, thank you for being here. Appreciate it. All the best for your revision. See you for whatever topic. This superposition, I think so. Okay, bye-bye. Have a good weekend.